Hi, the first thing I'd like to do today is differentiate these functions on the left to give the ones on the right, either in terms of dy by dx or f dash x. Please pause the video and try this now. Okay, hopefully you've had a good go at that. We're simply using a rule that we've learned previously, that if y equals x to the n, then dy by dx is n x to the n minus 1. We bring the power down, we subtract 1 from the power. We've shown that using first principles differentiation. We're not interested in doing that right now, we just want to use this rule. So if we just quickly skip through to the answers so you can check if you're correct. Here we are, we're just applying the rule. When we get to 1 over x, it gets a little bit trickier. We should write it in index form first and then differentiate. So you can give your answer in index form. Because they gave it as fractions, I've then written it as fractions. Make sure you can go between the two. Similar with the square roots, you need to write it as x to the half, and then I've written it as x to the minus a half, x to the minus a half. This should be an equals 4 minus 1 over 2 root x. So be aware that you can go from here to here as well. And then on this one, you have to expand the bracket first. Once you've done so, it's quite easy to differentiate. Okay, now I've got a second part of the task, so that's called differentiating. But sometimes we might actually give you the thing that has been differentiated and ask you to work back to the thing we started with. So what I'd like to do is just have a go at this. If I give you the functions that have been differentiated, apart from this one, then can you try and write down the things on the left? So pause this video and have a go at that. Okay, well done for trying that one as well. So going to the right is called differentiating. Going to the left is called integrating. They're opposites. Always in maths, we're interested in inverses, basically. If we can square something, it's useful to be able to square root. If we can raise something to the power for x, then we might want to take a logarithm. Plus and minus, times and divide. There's lots of examples. And differentiating and integrating another pair of examples of things that do opposites. And I think we've got our head around why differentiating is useful. It can be used for optimization problems. It can find the gradients of curves. It can find tangents and normals, stationary points. But why is integration useful? Well, we're not going to talk about that today, but it turns out it also has massive applications. So you've had a go at these questions anyway, and I'm just going to put the answers up and talk about them briefly. So we're sort of interested in something that differentiates to 2x. That's got to be x squared. So you might have done that using your knowledge of that, or you might have just sort of tried some different things until it worked. I'm not going to go into great detail on how you might have got to the answers, but see if you did. I think I've made a small mistake on this one. This one should be minus x to the minus 1 plus 5x. Apologies for that. Hopefully they're mostly correct. Do let me know if you disagree with any other ones. And then when we get to here, we are differentiating y equals x to the n. That's the rule we've just spoken about. But what if I just had dy by dx equals x to the n minus 1 without the n? Well, then it would be this. It would be x to the n over n. Because when I differentiate this, I'm going to times by n, and they're going to cancel. And then I'm going to minus 1 from the power. What if I just had my derivative as x to the n? Then in that case, it would be the same thing, but I'd be dividing by n plus 1. And I'd be actually adding 1 to the power and getting n plus 1 there as well. And you can see if we differentiate, if we use the rule we already know, if we differentiate y equals 1 over n x to the n plus 1, then I bring the power down, and that's going to cancel it. I'm going to lower the power, and it is, in fact, going to give me dy by dx equals x to the n. Two ways of writing it. You might write it with the fraction first, or you might write it as all divided by n plus 1. It's the same thing, but it's important to recognize that, and sometimes it might be advantageous to write one instead of the other. You might get these different situations where we need to be able to use them. The only other one we need to think about, just briefly, is that it's quite interesting that if we have y equals, say, 5, then dy by dx is 0. We've lowered the power technically on this x to the 0 to minus 1, and then we've times by 0. In any case, we get 0 as the gradient function. But if we then take 0 and differentiate it, then we also get 0. So a constant goes to 0, but then 0, which is a constant, but it also goes to 0. So there seems to be two things sort of that are differentiating to give 0, and that kind of creates a bit of an asymmetry. There's nothing that is differentiating to give us 1 over x. Because as soon as you differentiate 1 over x, it becomes minus 1 over x squared. So what is going on here? Well, we're a bit stuck, to be honest. At the moment, if we have dy by dx equals 1 over x, there is nothing that we can integrate it to. So it's going to leave you to think about that. We will, in fact, find that there is something, but that's for later on in the course. Okay, so our main topic today is integration in definite integrals. I've discussed what integration is. It's the opposite of differentiation. I've not said what indefinite integrals are, but this will make more sense when we do definite integrals. You've tried a starter, you've differentiated some functions, hopefully they've been okay, and then you've integrated some functions, and I've tried to get you to work out the rule yourselves. So, what is the rule? We know if dy by dx equals x to the n, then y equals 1 over n plus 1 x to the n plus 1. That's something we need to know. However, it's not actually quite right. I didn't go into it in the starter, but it turns out since we differentiate a constant to give 0, if I was to add a constant onto my function here, and the constant could be 5, it could be 7, it could be anything, when I differentiate that constant, it's also going to give me x to the n. Like if I differentiate the whole thing, I'm also going to get x to the n. So this is something we need to be aware of in integration. When you are integrating an indefinite integral, you will always add a constant, which we write as plus c. The only other thing to add is that, as I said before, this does not work for 1 over x, so technically we need to say that x is not equal to 1. Now, another way of writing this in integration language is as follows. We put this little curly symbol by the x to the n. We write a dx by it. This is saying I want to integrate x to the n with respect to x. It's doing exactly what I've done up here. It's just different notation. We'll talk about why we use that notation another time. And again, we get x to the n plus 1 over n plus 1. We need this plus c. Okay, remember that. And this is true for any n not equal to minus 1. So now we're just going to do 4 examples just to show this in use. The idea is that you've already sort of got your head around this, you've tried it. I think it does still take some practice, however. So I'm going to go through these 4 carefully. Some of them are a bit trickier than what I asked you to do on the starter. Okay, so let's do this. I'm just going to write around the page actually, so I think I've got space here. If I want to do this one, then I am first thing I'm going to do is I'm going to add 1 to the power. So because it's minus 3, that's going to become minus 2. And then I'll put my 2 in, and then I'm going to divide by my new power. Okay, so take this step by step until you get really confident. This is the sort of thing I'd like to see. Let's put the plus c in straight away so we don't forget it. And then that's going to equal minus x to the minus 2 plus C. Done. Okay, and something that's quite nice about differentiation, if you've understood it well, is about integration, if you've understood differentiation well, is that you can sort of check it. You can just think, right, if I now multiply by -2, I'm going to get 2. And if I lower the power, I'm going to get my -3. So yes, it's going to work. I can be pretty confident with that. Okay, onwards with number 2. I think I'm going to come down here for number 2. So if we integrate this, then I'm going to raise the power by 1. That's going to be 1/4 plus 1. That is 1 1/4 or 5 quarters. Generally good to leave your fractions as improper fractions for integration. And then we're going to divide by 5/4. And then we're going to plus c. Now that's not really a neat way of leaving the answer. Actually, when you divide by a fraction, it's the same as if we did 4/5 x to the 5/4 plus c. So this is my final answer. And once you practice like ones with fractions a lot, you should just get into the habit of just bringing down 4/5, recognizing that. Okay, number 3. Let's go over here. So for this one, we're going to need to expand the double brackets first. So I'm going to put an extra line, and it's going to be the integral, and I should have a bracket around the whole thing I'm integrating. 4x squared. Now you should be able to recognize that this is actually going to be the difference of two squares. I'm going to get my -2x and a plus 2x. I'm not even going to write those down, but I need to write down my -1. Okay, and that gives us our difference of two squares. So I'm integrating 4x squared minus 1 with respect to x. And now we're just doing what we did before. I'm going to do it slightly different. I'm going to sort of recognize I'm going to increase this to 3 and then divide it in the same sort of go. And so I'm using what I said before about I'm not putting the x over 3 here. I'm just putting it a fraction beforehand. It's the same thing. And then I've got -1. So that's going to become minus x. We know when we differentiate x, we get 1. We differentiate minus x, we get -1. Don't forget your plus c every time it needs to be there. Okay, last one, number 4. I think I've got space down here. So it's the integral of x to the 5 plus x to the 3 over x squared. Okay, I'm writing it down again, so then I've definitely got enough space. Okay, so we can't integrate this directly because it's a fraction, so we need to first of all sort of simplify it. And 2 ways to do that. If you're confident, you can just basically, cross that off, change that to a 1, change that to a 3. So it becomes x to the 3 plus x respect to x. If you're not super confident with that, let's just talk about it a bit more. So over here, so if I had x to the 5 plus x to the 3 over x squared, then I could first of all factorize out x squared from the top. I'm allowed to do that. X to the 3 plus x divided by x squared, and now it's a bit clear to see why it's sort of cancelling out to leave me my x cubed plus x. In any case, we're left with this, the integral of x cubed plus x, and now we're just using this rule. It's going to be 1/4 x to the 4 plus 1/2 x squared. I'm doing this in my head. I'm like adding 1 to the power and dividing by it in the same go. So if you practice these, get to be that quick. Hope that makes sense. So these are examples on indefinite integration. Have a go at some practice questions.